So simple linear regression is that scenario where you have one independent variable and one dependent variable. And as we can already see, if you look into the plot we have towards the left, that is when we plot two numeric variables, the total number of hours studied across the test score or the test grade, which is a numeric attribute. You can see it's a plot which resembles the correlation plot we studied in the previous modules. Now, the process of simple linear regression is to define the relationship as a straight line, which is defined as y is equal to mx plus c. Your y would be your dependent variable, that is test rate. X would be your independent variable, which is r studied. And c would determine the intercept, which can be, in a layman perspective, defined as the part of y which cannot be explained by x. I'll get into the details of a simple example, but then for now, let's understand what are the different terms in the equation. So the slope is basically the impact of x on y. Your m is defined as a slope and can, in a nutshell, be defined as a change in y divided by the change in x. Now, simple linear regression is the process where we find the best fitting line. So if there is a line that passes through all these points with the least amount of distance through these points, that would be determined as the best line. But then which line could be the best line? You could actually draw infinite number of combinations of lines and could call them actually as the best line. So you have a green line, you have a blue line, you have a brown line. And if you try to understand which is the best one, you can say blue line kind of looks the best line because it kind of passes through all the points with the least amount of distance from each of these points. Now, how do you determine the least amount of distance? That's when we have a technique called ordinary least squares. Let me give you a visual tour to help you understand this with a simple example. So, for simplicity, assume that we have two variables, the same one which we have been using till now. So this is the total number of hours, and this would be the total number of marks, right? And we could have different points over here. We could have a point over here, another point over here, another one over here, and probably many more, right? Now, if you look at the number of possibilities of lines that we could draw for this example, they are literally too many. So we can have a line like this, another line like this, another line, let's say like this, and many more. So which is the best line? How do you define that? We have a technique called as ordinary least squares. So let's say if you define the best line which has the least amount of distance from all the points that you see on the plot, we could actually calculate that with a simple metric. So let's say you are interested in finding out the distance of line 1. Let's call the green one as line 1, and then distance of line 2, and then distance of line 3, right? The black one is line 3. And let's say you get a metric towards the end. You say that a distance in terms of a simple numeric number can be defined as L1 is defined as 55 units, L2 is defined as 35 units, and L3 could be defined as 50 units. So you'll say that, okay, L3 probably looks the most promising one because it has the least amount of distance from all the points in the plot. Now, how do you calculate that? Let's just clear the mess over here. So let's say we are trying to plot a simple line. So just for simplicity, I'll draw a line over here, and you're going to find out the distance of this line. It's as simple as drawing a straight line from the point and then calculating the distance. So there could be some positive numbers, there could be some negative numbers. Now you take the square and add all of them. So you have 1, 2, 3, 4, 5, 6, and 7. 7 distinct points. And you can have a distance from each of those points to the respective line you're calculating. And if you add up all of these numbers, you'll actually get a positive number, the square of these numbers. So let's say this will be defined as D1, this will be D2, D3, this is D4, D5, D6, and D7. If you add d1 square plus up to d7 square, you get a number which will, let's say, represent the distance of all the points from this line. And the same process can be repeated for several combinations of line, and the line with the least amount of distance can actually be determined as the best line. Now this line will have an equation. That equation would be y is equal to mx plus c. Now m over here is actually the slope of this line. So if you remember, slope can be calculated using a simple formula. So you can have 2 points as, let's say, x1, y1, another point as x2, y2. Determining the linear distance between these 2 points, you can actually calculate the slope of this particular line. Now C would determine the slope intercept. So let's say this line cuts the y-axis at this point. So the slope would be determined as this distance. And if you remember, I previously mentioned, even though this can be mathematically defined as a line, as the point at which this line cuts the y-axis, it is also determined as that point of as that part of y which cannot be explained by x. So if we take a more intuitive example over here, let's say y is determined as height and x is age, and you're trying to understand um, height as a function of age. Generally, you observe that as you grow from during the teenage, height also increases to a certain point and then remains constant throughout your life. But then there is definitely a portion of the height which you can't really explain because so when a baby is born, let's say the age is 0, he would still have some height, and that height would be, let's say, 1 feet. I'm just putting a hypothetical number here. And then when he's 1 year old, he would have another number, let's say 2 feet. And when he's 2 years old, another number, and then so on. So this number increases to point, and then this remains constant. But then when he was 0, there was one height which couldn't be explained. Or let's say you're trying to understand the weight. When his age is 0, there will be some weight which he would have that cannot be explained. So that would be determined over here with the line. So let's say you're trying to say this is the best fitting line. This would represent the height or the weight of the baby when the age would be 0. And this would represent the age at age 1 and at age 2 and so on and at age n and so on. But then if you don't have the intercept, you kind of say when the age is 0, you don't really have a value for height, which is not the case. So that's the importance of intercept. So let's get back to our example over here. Now, once you have found out the equation, you can actually find out the value of y for an unknown value. You can actually find the unknown value for y when you have an appropriate x. So let's say for the same example, you want to find out, okay, what is the ideal score for a student who has studied for 5 hours? So you can actually leverage the same equation, and you will have, let's say, x as 5. So you can put in this equation and find out the value of y because you would have values for m and c. Now, one question which you would actually wonder, um, how is the best line calculated? We already have an answer for that, ordinary least squares. But since this is simple linear regression, where we have just one independent variable and one dependent variable, why don't we just use correlation? I just answered that question. It's the intercept. Because what if we want to define the relationship of y with x at x equal to 0 also? So if you just have correlation, when you say x equal to 0, you don't really have a value for y. Y is also 0, which doesn't really capture the part of the equation. So that's when we have regression, where we have the slope and we have an intercept also. Now let's move on to a little more complicated scenario, and that would be multiple linear regression. So real life scenarios will definitely have many more independent variables than just one. Now to model an equation that studies the relationship between a dependent variable and multiple independent variables, you can just extend the same equation which you have for simple linear regression. So I'll just make a small correction over here. It is m0 plus, yeah, now it looks better. So we're saying y is equal to m0. M0 is basically the value which would be the intercept, which represents c in the previous example. And then we have m1x1, which is basically the slope and the coefficient of the first variable, first independent variable, and we add the independent variables one by one with their respective coefficients. So we can say y is equal to m0 plus m1x1 plus m2x2 plus m3x3 and so on up to mn xn, where at any point we can say m2 would be the coefficient of x2. So just like simple linear regression, where we would say y is equal to mx plus c, where y is the same, mx would be the same as m1x1 and c is m0. The moment you have many more independent variables, you just linearly add them as m2x2, where each variable will have its own impact on y. If you look at the larger equation, we can say that it is an additive measure of all independent variables with its own impact. So if you have x3 impacts y by m3 and so on. So this is how we can actually determine an equation for multiple linear regression. So simple linear regression is actually too simple in nature. You won't really find tangible use cases for them in real life. Most use cases of supervised machine learning under regression will actually be a part of multiple linear regression, where you can just say the equation is determined as y is equal to m0 plus m1x1 up to the point mn xn, where n is the total number of independent variables. Now, we've taken a shot at understanding the theory of regression. So we've understood simple linear regression, and on the foundation of simple linear regression, we've understood with simple extension what is multiple linear regression. Let's take another step and see how we can code an example and understand this with the Python code. So let's move on to Spider to codify simple linear regression and multiple linear regression.